So in section 3.2, we are dealing with polynomial functions and their graphs. I am doing things a little differently than what is currently in the book, and we'll talk about that in class. But first, we want to talk about what is a polynomial function. Well, polynomial function is really most of the equations we deal with are considered polynomials. But as you can notice, they have powers 5, 4, 3, 2, 1. And when you don't have an x, we assume that's x to the 0 power. So your polynomial functions are going to have positive integer exponents. So therefore, no fractions, no decimals, no negatives. And you'll hear terms such as degree, which in this case, it's the highest power of any one term, which is 5. The leading term is the term with the highest power. So in this case, it's 3x to the 5th. The leading coefficient is 3. And these are my other coefficients, 6, negative 2, 1, 7, negative 6, which is also the constant term. Now, more examples of polynomials. 3 by itself is a polynomial, but the degree is 0 because you have x to the 0 power. We just don't write that. 4x minus 7, degree is 1. X squared plus x, degree is 2. 2x cubed minus 6x squared minus 10, degree is 3. And then we have one which is in factored form, which is going to be, most of the ones we're going to be dealing with are going to be in factored form in this section. And the degree is 3. And how do I get that? Well, we don't write ones on these factors, but we are assuming that the power of each factor here is a 1 because it's not written, and all the x's inside are 1s. So therefore, if we were to multiply this out and expand it to look like this, my leading term would be x cubed. So therefore, I can multiply it out, but I really don't need to because I can just add the powers of each factor. And that's how I get degree of 3. So there's some terminology. One of them is we start calling things zeros. And zeros are x-intercepts. They're called zeros because when we graph them, you'll see the 0 is certain x values where y is 0. Okay, x-intercept. So it's the same thing. All right. We also have factors, either x minus or x plus, whatever. And then we do the opposite sign is what we consider the 0 or the solution. Just like when we factored quadratics, we would factor the two factors and then our zeros or our solutions were the opposite sign. Okay, so in this example here, I want to find the zeros for x minus 2 times x plus 3 times x minus 1. And again, they are the x-intercepts. So the zeros I would find by using our zero product property. So my zeros are 2, negative 3, and 1. So it's the same process when we did quadratics. There's just extra factors now. Okay. Now, if I want to create a polynomial of degree 3 with the given zeros, well, I'm going to kind of take these and put them back into factored form. So remember, if r is a 0, then x minus r is a factor. So your factors are the opposite. So my factors are going to look like x plus 3 times x minus 2 times x minus 5. Okay, so that is how we can create the factors from the zeros and how we take the factors and give the zeros. So these are important because we will use these zeros to graph. Okay, and there's other information we're going to get from these zeros. So let's look at some of the information we need to be able to identify from polynomials. First of all, identifying zeros and their multiplicities. So, if you have a factor and you have a power, then your power is your multiplicity. So for instance, if this was x minus r squared, my multiplicity would be 2. Now, if your zero is of even multiplicity, that means the power of the factor, not the zero itself, then we can say the graph touches the x-axis at that zero. If the zero is odd multiplicity, then the graph crosses the x-axis. Okay? So that's one item. And you may say, okay, what's crossing, what's touching? I'm going to show you that here shortly. Okay? Turning points. How many times does the polynomial change directions? So the maximum number of turning points would be your degree minus 1. So once you determine your degree, the maximum times the polynomial graph can change directions is the degree minus 1. The third item is what's called the end behavior. And when we talk about end behavior, we're referring to as we choose values of x, or when we look at values of x that get very, very, very large. And at some point, many of your coefficients and your terms become irrelevant, and we look at just the degree of the highest powered term and with any leading coefficient, and that would be the end behavior. Okay, so for example, if we look at this polynomial here, I want to identify the zeros and the multiplicity. So zeros only have our terms with factors with x's. That 5 by itself is not a zero. So I look at this power, or this factor, it's x minus 2. It has a power of 1. So 2. And it has multiplicity of 1. The next factor is x plus 3. So the 0 there is negative 3, and it has multiplicity of 2. Because it has a second power. And then this factor here, the 0 is 1, and it has a multiplicity of 4. It has multiplicity of 4. Okay, so here are my multiplicities, and so if I want to know my degree, I take my multiplicities and add them together, which I get a degree of 7. And we'll use that when we determine our turning points. Okay, so let's look at here talking about where it crosses and touches the x-axis. So what do I mean by crossing and touching the x-axis? Well, let's just say, this is what our polynomial graph could look like, something like this, okay? So right here, 1, 2, 3 locations are considered crossing x-axis. Right here, and right here, because they go from negative to positive, positive to negative. This point here is what I would consider touches the x-axis, because what it does is it approaches, it lays on the axis and goes back the same direction it came from. So you've got a difference in where a graph crosses the x-axis and where it touches the x-axis. And we can determine that based on the multiplicity. So we go back up here, odd multiplicity, the graph crosses the x-axis at that 0. Even, it touches. So for this polynomial we just looked at, the graph crosses the x-axis at x equals 2. The graph touches the x-axis at x equals -3 and x is 1. So it touches at these two intercepts, crosses at that intercept. And it's all based on the power of the factors. So what we're going to do, we're going to use all this information to assist us in making the graph of these polynomials. Determine the maximum number of turning points. Well, it's the degree is your n. So it's as we set up here, n minus 1. So degree is 7. So 7 minus 1 equals 6 possible turning points. Doesn't mean it's going to have them. That's just the maximum number it can have. And then the last bit of information we want to get is the end behavior. The end behavior, again, would be if we multiplied this out, it would be our leading term. Now, if we were to multiply this out, it would probably take a whole sheet of paper because you got x minus 1 to the 4th power, x plus 3 squared, you're multiplying and all that. We don't need to know that because our end behavior is in this format. N is your degree, A is your leading coefficient. So the end behavior for this one is 5x to the 7. So we know if I was to multiply that out, that would be my first term or leading term. So that's getting the information. Now let's look at graphing the polynomial. So what I'm going to do to graph, first I find the zeros and the multiplicities, where it crosses, where it touches. I go ahead and plot my zeros along the x-axis. Then I create a table of values, and I include points from each interval in the table. And these points determine where the graph is above and below the x-axis. I determine the end behavior, the maximum number of turning points, then I sketch a smooth curve. So let's look at a few examples. Okay, so I'm going to analyze the graph of x plus 2 times x minus 1 times x minus 3. So my zeros are -2, +1, +3. All my multiplicities are 1, so it crosses the x-axis at all of them. So that's the first thing we determine. Make sure I'm following my own notes. Okay. Step 2, I plot the zeros. Sorry, my writing's sloppy. So I plot -2, +1, +3. So these are zeros because here's where x is -2, y is 0. X is 1, y is 0. That's why we call them zeros. Now, third thing I'm going to do is I'm going to create a table of values. And I list my zeros, leave a space in between each one, because I'm going to find points in each interval to determine positive, negative, above or below x-axis to help me sketch this curve. Okay, So I'm going to choose x is -3. The best, always choose 0 if possible. Okay, so -3, 0, +2, +4. Now, the way we find points, it doesn't matter what type of equation you're given. You substitute x into the equation and find y. So just for time purposes, I'm not going to go through each one. I will show you more in class about this, but it wouldn't hurt you to pause and try it yourself. Okay, I'm putting -3 in for each x. Okay, I'll show you the first one, and then after that, I'm just going to just fill in the numbers. Okay, so if I find p of -3, -3 plus 2, -3 minus 1, -3 minus 3. Okay, so this gives me -1 times -4 times -6, which is -24, and that is below x-axis. So I am not going to scale my y just because the numbers can get very large, sometimes very small. All I know is at some point this graph is down in this area. Okay. When x is 0, I get 6. So again, I'm going to plot it somewhere. I'm not going to worry about it too much. I'm just going to estimate where I think it's going to be. And this is above the x-axis. When x is 2, I get -12. Excuse me, wrong. 4 times 1 times -1. How about -4? Sorry about that. And you know, that's kind of somewhere about in here. So again, I'm just estimating, and I'm more so concerned with where it's positive, where it's negative, not so much than the values, okay? Because I'm just making a rough sketch. And then when x is +4, so I get 6 times 3 is 18. So I get 18, and this is also above the x-axis. So at 4, it's like somewhere up in here, okay? So I've got my table of values, got my points plotted. I'm going to go ahead and skip to the sketching a smooth curve since I've got everything. And what you're doing is you're just making mini U's in between each one of these. Okay, doesn't have to be perfect. All right, we're just sketching. And so that's what your graph's going to look like. Okay, and you've got a hump here and a hump here. Okay. So that's number 6. Number 4 is my end behavior. Don't forget your degree is 3. And my leading coefficient is 1 because there's nothing up here but a 1. And then my turning points are going to be 3 minus 1, which is 2. So my maximum number of turning points is 2. So one thing you may have gained out of this, or you may not have, is, you know, if you look at that it crosses the x-axis, and once I found this point right here, I kind of knew that it's going to cross, go up, come back down, cross again, and go back through like that. And so for sketching purposes, that's, you know, you can kind of tell how it's going to go. Okay, so that's, you know, one possible example. Another example of what we can do here is when we have an x by itself and then we have a square. Okay, so if I look at this one here, my zeros are 0, 4, and -1. So this right here, it's not 1, it's 0. Now, it crosses at 4 and -1, and it touches at 0 because this has an even multiplicity. Okay, now number 2, I'm going to plot the zeros. Okay, so I'm going to plot -1, 0, that's kind of tight, and then 4. Okay, so that's kind of tight, and it's unfortunate for us. Our table's going to be have a fraction in it. I know that's bad, but it's not impossible. So when I make this table of values, I've got 0, 0, and again, I know this is 0 because it's an intercept. Okay, oops, forgot my -1. Sorry about that. -1, 0, 0, 0. 4, 0. Okay, so I'm going to choose -2, -0.5, got to do it, +2, and +5. So I'm going to fill in my table. And again, you can pause this and double check your math, but for time purposes, I'm just going to do this in my head. Okay, so if I do x is -2, -2 squared is 4, -2 minus 4, so make sure you're squaring properly. -2 minus 4 is -6, so that's +4 times -6, and then times -1, which is +24. And that's above the x-axis. Okay, now when I do -1/2, I'm going to have to do a calculator for this one. I don't even want to think about that one in my head. I mean, I could do it. I just don't want to. All right, so, and I don't know if I trust my calculator or not. We'll see. All right, so if I do -0.5 squared, I know that's +0.25 times -4.5 and then times -1/2 plus 1 is +1/2. So I'm not as concerned with the numbers. I'm more concerned with positive or negative because I want to know where it's below. Okay, so again, this is above, this one's below, and again, if we want to, we can plot them as we go. We just know it's above, this one's below, and I'm estimating, that's all. Okay, I'm going to check here at 2. So if I let x be 2, 2 squared is 4, 2 minus 4 is -2, 4 times -2 is -8, and then times 3 is -24. So this is somewhere down in here. And that's true because it touches here. And I'm going to show you what I mean when I draw that. And then when x is 5, so you're going to see one that gets really, really big here. Okay, so at x is 2, we got -24. And then at x is 5, 5 squared is 25. 5 minus 4 is 1. 25 times 1 is 25. 5 plus 1 is 6, so I get 150. And again, I'm more concerned about the fact that it's above the x-axis. I'm not worried about these actual numbers themselves. I want to know above and below. So then I sketch my smooth curve. So you're coming down here. You touch, go back the same direction, and then go up. Okay. You're only going to touch or cross at intercepts, so don't be crossing where there's no intercept. So what you're doing between each intercept is you're making a mini parabola, okay, a mini parabola, all right? So, that's how we graph it. We'll do more of these for practice. Your end behavior. y equals x to the fourth, because my degree is 4, 2 plus power of 1 plus the power of 1 is 4, and then my turning points are 3. Move this up here. So we will be doing more examples of these. But I just want you to make sure you kind of get the gist of it. Like I said, the book, I'm doing things a little differently than what they're doing in the book, but it's all right. So that is it. Another long one.